Good morning, everybody. I'm Samir Sankalna, representing the Department of Physics, University of Colombo. Welcome all of you to the webinar of radio frequency application with microwave wizard. I would like to introduce the guest speaker for today, Ms Thejani Fernando, alumni of University of Colombo, Department of Physics. She is hold a BSc honors in engineering physics and holds a MSc in communications systems and electronics in Jacobs University, Bremen. Currently working as an application engineer at Mician GmbH. Over to you, Miss.
Yeah. Okay, so good morning, everybody. I'm Thejani. I'm a batchmate of Monica and Lakmal. So today I'm here to introduce you about RF engineering. So I'm an RF engineer since 10 years now. So I did my master's in Germany and then in electrical engineering. And then thereafter, I joined a company who is selling a software related to RF and microwave components and systems. So today I'm here to share my knowledge with you guys. Yeah? So let's start from the beginning. So here, I'm going to give you a brief introduction about RF engineering. And then thereafter, we will go through how to operate our software called Microwave Wizard. So let's take a look. What is RF engineering? Do you have any idea about RF engineering, and have you heard about this before anywhere and so on? But I think everybody is using a mobile phone right now, right? So this is one example for RF engineering device, right? And this means RF engineering is a specialized branch of electrical engineering. So here, all of you are doing physics, but physics is the base for any engineering aspect. So this does not mean that as you are a physics student, that you are not capable of handling electrical engineering stuff or something like that. I did my bachelor's degree specialized in engineering physics, and then thereafter I did my master's in electrical engineering. But all the theory are what I have learned in bachelor's. They are all connected. So RF engineering means, as you can see there, it's a branch of electrical engineering. And in other words, whatever system or a device which fall inside the frequency spectrum from 3 kilohertz to 300 gigahertz means RF engineering. So in other words, we call RF and microwave engineering. So RF means radio frequency. So yeah. And I will further explain this to you in terms of an example. This is a system which has been designed by one of my colleagues in Germany for highly integrated RF transceiver design for mass production. So this is huge. You don't have to take it on your head. Oh my God, this is so complex, and this is too much, and so on. But it's not like that. Everything has been constructed from scratch, from the basic building blocks, and it ends up something like this in the end, a complex design. And it is, it's a transceiver. Transceiver means it is composed of a transmitter and receiver together, and includes an antenna as well. So you can see it there, and there are a few layers. So the antenna is on the second layer, but I don't know, for some reason in Zoom, they don't see their mouse, I think, but it doesn't matter, right? But I can explain it. Here it's the same, but okay. So now you can see what I have pointed out is the antenna. This is called a patch antenna array. I will come to this point a little bit later. This is just an example of how an RF system looks like in the industry, right? And then the far behind, you see somewhat complex circuit design. And this is the major construction part composed of RF components. And here you see the block diagram of such a transceiver design. And there maybe some parts are familiar to you, like you see the, okay, the resolution is not so, because the picture is not very quality with the resolution, but yeah, you see the transmit amplifier and then low noise amplifier. I think they are somewhat familiar to you because we are learning about amplifiers during our bachelor's. And then in addition, there are output filter, input filters. So then filters are a major role in RF engineering. And then the antennas. So here this transmit antenna and receive antenna, and so altogether this represents one of major RF system, and this has been designed for mass production. And this is very specialized because this is very compact, and this has been constructed fulfilling all the customer requirements and everything. So in the next picture, I will show you the real assembly of this such kind of a system. And you see in few moments later, I will introduce our software microwave wizard to you. So then you will be able to, you are capable of designing such kind of design, which you can see on the left-hand side of this assembly. These kind of components can be designed using such kind of a software. And this is essential nowadays because when you have a requirement from the industry, then you first have to develop a sketch like in the left side, and then you need a software to design such a circuit, and you need a synthesis algorithm to develop the functionality of such a system. According to the frequency aspects and the performance requirements and so on. And then for all those things, such kind of a software can construct the components according to the space requirements and the frequency requirements and performance as well. And then later on, you can optimize the system to meet the final desires. No? And then the rest of the part is, I think you are somewhat familiar, at least Lakmal is familiar about those things. So they are simply integrated circuits, and the remaining part is the power handling and the other system, the matching components and so on. So this is this is one of the examples. I just wanted you to know how an RF engineering is applying in the industry. So I just made the reference. This is my colleague, so he is quite a expert in our field. That's how I grabbed that reference. Okay, now we come to applications of RF engineering. So you should know why you study this field. This is a very emerging area nowadays. So, this is applicable in cellular networks. As I said, all of you have a mobile phone, and in your mobile phone, there are several RF components. So, and then the radio and television broadcasting. That's how we knew the first word, radio frequency. So from our radio and television broadcasting, and then widely used satellite communications. So you know that. And then the radar systems in terms of radiation, in terms of several antenna systems around the world, and then space and defense systems. So you know, everywhere in the world nowadays there are wars and the things. So this area is widely used in this space and defense systems. So it is a highly confidential area as well on one hand side. So yeah, and now we take a look at, so you can interrupt me if there is anything you do not understand or if it's not clear and so on. Yeah, so let's take a look. What are the key roles of RF engineers? As an RF engineer, what you have to do? Basically, you have to design and develop such kind of components, which lies basically, as I said before, between this frequency spectrum, 3 kilohertz to 300 gigahertz. Those components you have to design such antennas, amplifiers, and transceivers. A transceiver example I showed you in the previous slide. And then you have to ensure the transmission and reception signal are efficiently transmitted or received. And then, and you have to optimize the system performance. So you have to use your techniques to improve the performance. This is also everyday developing field. Now artificial intelligence has come to this field as well. This is the most modern era with artificial intelligence. So when it comes to optimizing, now the trending is going to this artificial intelligence. And otherwise, so you have to, at the same time, you have to reduce the interference and you have to improve the quality of the signal. So these are the main roles of an RF engineer. Okay, I think all of you are interested of when we study something, what do we have the opportunities next? No? So as a bachelor student, I had the same question when I was studying a student like you. Okay, what would I do after this? No? So to be honest, when I was doing my bachelor's, I also studied several theoretical subjects and the things. I had no idea of what I would do next. So I was like studying everything, but I was quite blank. Okay, what would I do? So with this bunch of subjects and so on, sometimes I had the feeling, okay, why I'm learning this much of different areas. But now I know, after I think about 15 years after having getting the bachelor's, I know that each and every subject is usable time to time, and it's not everything that we will be able to use in our career life, but sometime at some point they will be useful. So you don't have to keep it in your memory everything, but when you need it, then it will come to you. So when you learn it in your bachelor, so don't worry when you learn something and when you don't know that what would you do it in the future with the subjects that you are learning, but it will come to effect some years later. No? So like with me, now it has been 15 years, but they are very useful for me nowadays. So what I have learned. So the career opportunities, telecommunications. So as I said before, everybody has a mobile phone right now. It is widely used in cellular networks. So you see there's a very good demand in this area as a career opportunity. And then the broadcasting, radio and TV broadcasting, it is widely used. And then the satellite communications. Satellite communications is also now somewhat expanding around the world. So it has a good trend in that area as well. And as I said before, defense and aerospace. in the aeroplanes and for designing sensors and the things. So for example, I'm working in Germany, and Germany in my area, which is called Bremen, they are developing. They have a special plant for manufacturing Airbus. Airbus, you know, the Airbus flights. They are designing the sensor part, sensing part, which means on the sensing part of the flight. So likewise, in different cities around Germany and France, they have they are designing different components. All are related to RF engineering. And then consumer electronics. Once again, consumer electronics are related to the cellular networks, mobile phones, and so on. And then research and development. So this is always a developing area. So this is all the ongoing research are always presently they are widely used. So in universities and so on, it is very encouraging field, because this is not very, this does not have a big history, this RF field. So this is quite new, and the experts in this field are not very old. So like I would say maybe now the experts in this field are in their 80 years old and so on. So it doesn't go that beyond this subject. So this always has new opportunities for you. So then the young people like you are very much welcome in this field, because it needs new ideas from the young generation. And then the healthcare. So you know, there are lots of development, especially in the cancer treatment area and so on. So the radiotherapy and so on. So then again, this is used more widely than before. So then education and academia. So I don't have to introduce about this to you. So now you are learning. So likewise, this has always has a very big demand. Okay. Now let's take a look at key components of RF design. So what are the basic building blocks of this kind of RF design? Antennas. I think all of you are learning electromagnetism, electromagnetic theory, and then up to dipole antenna, you are learning the theory. So this is the basement for RF antennas as well. So antennas is one of the main basic building blocks of RF design. And then amplifiers. Amplifiers also so you have to amplify the signal. Power amplifiers you have to use to amplify the signal when you radiate it, and then when you receive a signal, it is very weak signal, and then also you have to strengthen the signal, so you need amplifiers, and otherwise you have to suppress the noise which comes. So then low noise amplifiers are used. And then filters. I have bolded it a little bit more because I'm going to talk much more details about RF filters in this presentation. And the filters are widely used because in any RF system, they are operating, they have a defined frequency spectrum. So they have some kind of frequency bands. So you always need a filter to grab the signal which is dedicated to this the required frequency band. So or else you need to suppress low part of frequency, low range of frequency, or else in the other words, high range of frequency you have to filter out. So for in any case, you need filters. And then the mixtures, because sometimes you may need to combine 2 or 3 channels together. And then, yeah, you need to, it is also, yeah, for frequency conversion and so on. So you need mixtures and oscillators. I think oscillators we are learning anyway about the theory, you know, what is an oscillator. So here, the theory is the same, but the application is a little bit different. Sometimes maybe the oscillator, you may have practically implemented a little oscillator during your lab sessions. And then this is the same theory applies to RF engineering as well. But the only thing is you may have to design it in a different way. So likewise, the oscillators are one of the basic building blocks as well. And then transmission lines. So if you learn RF engineering, you will have to learn a little bit deep into transmission lines. There is a theory called transmission line theory. So S parameters and so on. So this is this you will have to follow up a little bit. I will come to this point a little later with some examples. Yeah, and then yeah, you have to when we talk about transmission lines, the signals are transmitted through either coaxial cables. You know, coaxial cables. We are using it in our PCs as well, or else microstrip lines. I don't think that I have to introduce about microstrip lines to you. I was very big. Yeah, I really liked the microstrip, working with microstrip lines when I was doing my bachelor's. So I think same with Lakmal as well. And because in our physics degree, we have a bit more practical knowledge about designing and printing PCB designs and so on, right? Or either waveguides. This is this may be waveguides may not be familiar to you. Waveguide means another source of transmission of signals, especially the microwaves. And this can be a piece of metal or something like that, or in the piece of metal tube like that. So it looks like just like a Sloan pipe, but inside there is a design. So for that you need a software like Microwave Wizard, which I'm going to introduce to you. But the waveguides also a kind of a transmission medium, like coaxial cables and microstrip lines. But especially when we talk about microstrip lines and waveguides, if you handle low power circuit, you can yeah, you can construct your design with microstrip lines. But when you need a very big system like in satellites and so on, you need to handle high power. So for that, you will need quite a thicker medium of transmission like waveguides. So with in terms of thicker metals and so on. So for that, we are using waveguides in the industry. And then duplexers and duplexers. So as same as mixtures, we combine or separate frequencies. It's also quite similar, the duplexers. And duplexers, they are also used to separate or differentiate two frequency bands with in the same system. Yeah. So those are okay. There are okay. Again, phase shifters and switchers. They are also yeah, some kind of basic building blocks. And okay. Now let's talk about one of those basic building blocks in RF engineering, so-called filters. I am more, my application knowledge is more involved through filters in the past. So I think I would explain this more better to you. Yeah, so as I said, it's one of the basic building blocks in RF engineering. And basically, there are three major tasks. So you are using a filter either for channel selection or smoothing a signal or for impulse generation. So on the right-hand side, oh no, okay, your right-hand side, yeah, my left-hand side. So you see a frequency response of a filter. So in general, so this is a bandpass filter. You see there are some, yeah, we call poles and zeros here. Are you familiar with poles and zeros? I'm not. I don't remember if we studied about them in applied maths or so. Huh? Yeah, if you are familiar with poles and zeros, so in the filter response, poles and zeros are represented by those spikes in the pass band. So the requirement of designing a filter is you are basically you are given this frequency response or so-called coupling matrix representing this frequency response, and your task as an RF engineer is to design your component, your design, which fulfill this response in the end. So simply combining 2-3 components together will not give this response. We'll need some days, sometimes some weeks to get this kind of response. So it's a little challenge, but this is what you have to learn, and this is what this is what will be usable in the future. So, and here you see this frequency response on the bottom axis. It represents the frequency in gigahertz. So here this filter has a center frequency around 3 gigahertz. It's a 3 gigahertz filter. And then on the left axis, it is the S parameters in dB. So this is the frequency, the response about S parameters against frequency. And the gray line means S to1 response, and then where the return loss is given by this purple line with poles and zeros, which is S11. Okay, so this is another, there are basically 4 types of filters. I think this is nothing new to you. Low pass filter, high pass filter, band pass filter, and band stop filter. I think in lab sessions you covered them. So that's the same thing hold for any, no matter whether it's RF engineering or anything else. Filter is the basic fundamental of filter is a filter. So here is a further explanation how a filter is used for channel selection. You see, when there are several channels comes together, and when you want to extract only the middle channel, you are using a bandpass filter. Then the output will be containing only the middle channel, suppressing the on the channels on the left and right side. So this is called the channel selection. And the second one, for smoothing the signal, you are using a low pass filter. When you use a low pass filter on your system, then you can smooth your signal, avoiding canceling the noises and so on. And then you are using a high pass filter when you want to use the system for pulse generation or as an integrator and so on. Okay, this is not a simple design. It's a quite a complex design, but I have the heading. I have stated a simple filter design without any synthesis tool. Means this is what I'm gonna introduce you with our software, how you can design a simple filter which is a part of this complex structure, and using the software. So at the moment I have our company software called µWave Wizard. There are other softwares in the market like HFSS, CST Studio, and so on. So in any software you are using these kind of softwares to design some kind of structure like this. Either it's a complex or a simple. You need a software to design it, because this is a software means what you are learning in the theory as electromagnetics right now in your bachelor's. This is integrated in a software. So then you can use it as a graphical user interface. So in a simple filter design, you will set up some, we call it irises, and I will show you how to do it. And you are designing a cavity. We call a cavity. Cavity is one component of a filter, and when you combine 2-3 cavities, you come up with a complete filter. And then constructing the filter is the first step, and thereafter you have to tune the filter in order to meet the specific requirements, frequency requirements, like a specific frequency band or rejection and so on. And then for accuracy, you are using 3D FEM. It's a solver. You are using a solver called 3D FEM. So when you're using different solvers, our software is capable of using different solvers, and you can compare the accuracy of the of our design. So 3D FEM means you simulate your structure in a mesh. So you are mesh wise. So that's the idea behind it. So, okay, now I'm gonna introduce a little bit about our software, how the software is operating when designing any kind of RF component. So ours is so EDA tool for designing and optimization of passive microwave components, including antennas. We have a hybrid solver concept, as I said before. There are several solvers. If you go deeper into this subject, you will have to learn about those solvers. So we have mode matching solvers, and then this so-called 3D FEM or 2D FEM and so on. So mode matching means, I think this may be a little bit familiar to you. In electromagnetic theory, you are learning about the modes of propagating wave, and then when we design, let's say, a filter, so you are all, working with propagating signal. So then in this propagating signal, there are propagating modes, and then from the input to the output, you are matching these modes, propagating modes. So this is the mode matching solver. And then in 2D FEM, your design, you bring it to a 2D plane, and then in the 2D plane, you create a mesh, 2D mesh, and there you match your input and output requirements. And then in the third, the 3D FEM, you create a mesh for your complete design in 3D. And then there you are matching the input and output requirements. The 3D FEM is the most accurate solver so far, but this is this is very time consuming. So we are using a hybrid solver, combining 2-3 solvers together. So then we can, at the same time, we can improve the accuracy, and then we can save the time as well. So we have in our software, we have a huge library containing several elements which is usable of constructing this kind of components: antennas, filters, multiplexers, and so on. So this is another representation for what the available solvers in our software. 2D FEM, this is boundary control mode matching, FEM, 3D FEM, and so on. So then when you use, so you see it on the screen. For each element, you are using a different solvers, and then, but in the end, you integrate all the elements together to construct the final design. It is a filter. So you see on the bottom, it's a filter. So, okay. Now I'm going to use the presentation in parallel with our software. So I think some of you also, yeah. So if you have installed µWave Wizard on your computer, you can double click on the icon. It must be visible on your desktop. And then you will come up with a window like this, which you can see on your screen now, right? So, has everybody got this window as on the screen? Yeah. Otherwise, you have to interrupt me, okay? And then when you come up with this µWave Wizard Start Manager, you have several possibilities. You can open an example. If you click on Start with an example, or the Start Assistant, or you can click on From Scratch. So when you are an experienced user, then the user always prefer starting from scratch. So that this window will not bother you, and you can do whatever you want. But as a beginner, we always recommend to start from Start Assistant, because the Start Assistant set up the project for you, yeah, with necessary requirements, prerequisites. So we click on Start Assistant, and then the Start Assistant will show up. Yeah, if anybody gets stuck somewhere, so then please interrupt me. Yeah. So here you see the first window. You have to enter a name for the project and the location for your project. So I would recommend you for the first project, give the project name, okay, whatever you like. I will call it my project. And then give the location. I will set up the location as desktop, so you can do the same, because later then it's easy for you to find it, and then you can click on next. There you can set up the geometry dimensions. Here you can choose between several units. So we are widely using millimeters. I'm not sure. So in US they are using inches. I think here we are also using millimeters. So keep it as millimeters, and then click on next. And then the circuit name. So the circuit name appears as the project name followed by underscore main. So you can leave it as it is. And then it comes to the frequency range. So on the on your right hand side, you see there are several frequency bands which are available. So they are the sum of the frequency bands which are used in the industry. So I would use, for in this example, I'm using this KU band. Yeah, if you search through it, you can see the start frequency is 12.4 gigahertz, and it goes until 18 gigahertz. So you have to double click on this frequency band. Then it will take the those values into the those text fields. Start frequency, stop frequency, and the number of steps. That means the number of frequency steps which is taken by the software to generate the frequency response. I would set it up as 501, because 101 will give you a somewhat coarse response. So 501 is sufficient. And there is another button called adaptive frequency sweep. If you click on that, you can change the sweep type. So by default, it is the normal sweep type, which means the frequency response will go through every frequency step and then create the response. But if you click on adaptive, the frequency response will be generated according to adaptive analysis. So the adaptive analysis is much faster than the normal sweep. So we will choose adaptive. And then the remaining settings are not very important at this step because they are some advanced settings. So you can keep it as it is, the rest. And then you click on OK. Later you can go through all those advanced settings. So they are all comes with a description in the help manual. So, but for now, let's go through the most basic steps. And then you click on next. Then you come to the waveguide modes. So there you have to enter what is the highest cutoff frequency and what should be the highest connection frequency. So when I come to the design, I will show you. I told you that a filter means a combination of cavities, several cavities. So when you connect one cavity to the other, you need to consider the analysis up to a certain point of frequency, the analysis for the accuracy. And then the connection between two resonators, you need somewhat a lower number of frequency steps, so which means the connection frequency. So as a beginner, you don't have much idea about how you choose these values. So this comes with the theory in a way, and on the other hand side, this comes with the practice. So that's why we introduced this start assistant, because this, depending on the waveguide you choose, it predicts the starting values for you. So you can keep it as it is. And you can create some variables for future use. So you can tick this create variables for the cutoff frequency. So if you are not satisfied with the response, you can play with these two values to improve the response, especially regarding the tolerance. This is important when you play with the design in the end to see the tolerance for higher frequencies. And then you can click on next. And now it comes to the symmetry. So the filter which we are going to design is a symmetric filter. I will show you that. Yeah, okay, I can show you now. So, down. So if you see it, if you see it on the right hand side, that's the filter which we are going to design now. So you see it has a symmetry. It is symmetrical in the XY plane and so on. So that's what it is. The software is asking if your design has a certain symmetry. So you have to provide the symmetry. If you keep the symmetry none, then again the software will compute the design and analyze the design, but it will take double the time than when you are setting a symmetry for the structure. So as I'm more familiar with the software, I know that there's a symmetry. So for now, I would like to change the symmetry from none to different symmetry. So here we call our filter is H-plane symmetric. So host muted me. Why? Okay. So okay, yeah. So so you have to set up the planarity H-plane. So because as you see on the right hand side in this window, symmetry editor, the waveguide, the filter, is symmetric around H-plane. So these things you have to cover in some sessions of theory regarding the H-plane or E-plane and so on. I think we are covering it somewhat in electromagnetic theory, the H-plane structures and E-plane structures. They are different to each other in terms of modes, propagating modes, right? So here, what we are going to design, this filter is symmetric around H-plane. So I set up H-plane symmetry, and then I click on OK, and then you click on Next. Yeah, and then you come up with a standard waveguide housing for your design. So here you have to choose what kind of a standard waveguide you want to use for the input and the output, because I think Lakmal was also having the concerns how you match the components. So in the manufacturing, there are some standards. So for the structures. So if I click on this edit waveguide, you see, okay, it's not expandable. These are the standards. So either your waveguide structure, I told you, sometimes it looks like a echelon tube, or sometimes it looks like a rectangular tube or something like that. But this has a standard in the industry. So these are the so-called standard IEC, EIA, or RCSC, and each standard represents a specific dimension and the frequency range. So this Start Assistant by default, it can choose a standard waveguide depending on the frequency range you have entered at the beginning. So as I said, I entered a KU band frequency. So according to the KU band, the standard is WR62 waveguide, which means it has the dimensions with a width with 15.799 millimeters and the height 7.899 millimeters. So this is standardized. So you can choose this one, or if you want to design your own design, you can specify your dimensions by your own, and then at the same time you can give your frequency range. So for this example, I will keep the WR62 waveguide as it is, and so I do not create variables because it is already ticked. So I click on OK, and then this the waveguide type will be set to WR62 with A1 and B1 variables. So then I have ticked this create variables for waveguides. So then in the end, the project will come up with set up with variables for the dimensions. And then you click on next. And here you set up the material. So again, you can see some description on the left-hand side. You can go through it later. So you for your material of the waveguide, mostly they come up with aluminium or copper and so on. But for the simulation, we keep the ideal parameters. Later, at any time, you can change the material settings. But it's easy to start with the ideal parameters, and then later, when you come up with a optimized design, then you go to material parameters later. So then you keep epsilon r and mu r as 1, and then metal as ideal. But if you know what kind of material you are using for your design, then you can set up the material as you can see it here: silver, gold, copper, or something. For now, I keep it as ideal. I tick off this create variables for the waveguide because you don't have to play with the material parameters right now. And then click on next. And now you have to set up FEM settings, the 2D discretization and 3D discretization. This is not very important for this example because we are going to use mode matching solvers. For mode matching solvers, you are not playing with discretization, but later for comparing the accuracy, you will need 3D discretization. So you keep the default settings as it is because you are a beginner. So then I click on next. Okay, then you can choose between several add-ons at this step, or you can proceed with the empty project with all the pre-settings. So you see there is a filter assistant, taper assistant, and so on. And here you see several antennas. There are macros for several antennas. But at this point, I'm not going to use any tool here. I'm going to teach you how to design the filter from the scratch. So once you, now you are done with your pre-settings, and I have to look if I missed anything here. So now you have to, one more tick. You have to tick on create elements here. And then you can click on finish button. So the project has been created now. Still you see it's empty. But on the left hand side, you can see the project panel. And there, if you expand the frequencies, you see our chosen frequency range has been set. And then if you expand the variables, you can see the variables. 4 variables has been created, for 2 for the cutoffs, and A1 and B1. So altogether, you should get 4 variables if you have followed everything correct. And then there must be one circuit designed. If you expand the circuits node, there should be a circuit called My Project Main. So you can double click on this. And then, you should get an empty schematic if you double click on it, right? And now what we're gonna do is, we are going to make this design, which is a cavity. We are going to implement a cavity on the schematic now. For that, you need to add 2 ports as µWave circuits. We are widely using 2-port networks. So it can be 1 port or maybe 3, 4 multi-ports as well, but widely using 2 ports, so input and output. So you're going to need 2 ports, which is you can see on the screen as red circles. And then you're going to need, we call it iris. Iris is represented by, in this 3D viewer, the small window on both sides. And this purple rectangles are the ports in the end, input and output ports. And the irises are the little windows next to the port. And then you see the yellow rectangle, that is a cavity. So this is the, altogether, it's a representation of one cavity as a one part of as the, a part of the complete filter. So when you combine these cavities, 2, 3, 4, 5, and then you come up with a filter of your desired order. So basically, the connecting number of cavities are equivalent to the number, equal to the order number. So we say 4th or 4th order filter, 5th order filter, 6th order filter, and then if it's a 6th order filter, you're gonna need 6 cavities for the 6 resonances. And now let's design this schematic on your empty schematic diagram. So let's go to the project. And now you see on the project panel, on the bottom of the project panel, there is a tab called libraries. Under the library, you see there are so many building blocks. So if you expand, for example, the first node, it's called belts. These are a number of belt diagrams. You know, belt means a belt, which you are using in a corner of a system. So it's an example. So you can choose different kinds of belts here according to your desired design. So here we're gonna need what it is called irises. So if you find the iris node, you have to expand it, and then just go down through the irises library, and then you find something. The symbol is somewhat similar to H, capital H, which is a rectangular iris in a rectangular housing. It is called R1R. The description is rectangular waveguide with a rectangular iris. This is what we need. So click on that, left mouse click on that, and then come to the schematic, move the mouse pointer to the schematic, and then click on the left mouse click again. This will place this iris component for you. And then once you click on that, on the right hand side, you have to, okay, once you click on that, just double click on the element, and then so-called element editor will appear on the right hand side. And then you have to set up the parameters for this iris there. And since we have the start assistant have done all the pre-settings, including the cutoff, frequency, and the symmetry, all are preset to the project for those elements. So you don't have to do anything for those things, but you have to set up the port geometries and the other iris geometries. Now, under this element editor, you have to search for port properties, and you see there are A1 and B1. A1 and B1 are your port dimensions. And you remember we have chosen a standard waveguide having A1 and B1 as variables. Now you have to give the same variables for here as well. So I'm going to type A1 in front of A1 property and B1 in front of B1 property. And then for the A2, I will follow the same instructions as a presentation. So you have to give A2, okay. For in front of A2, type A2 and press enter. Then you will, because this A2 variable is not defined in the project, so then you will be asked to create a variable for this one. You can give a value directly inside, or you can type a letter there, so then it will ask to create a variable. So for this one, give the value as 8, for example, and then click on OK. And then the A2 value will be set in this iris. And for the B2, give the value as B1. So we keep the B1, the height we are not going to change. We're going to keep as the port height. For the thickness. Thickness of for the iris, there has to be a certain thickness. That's what you have seen on this, because this iris has a little thickness. So in front of ZL parameter under the geometries, type ZL, same like the parameter name, and then click on enter and give 1 for the value, and click on OK. And now we are, so the rest of the parameters are not very important. They are for advanced users. For our task, this is sufficient, and now click on apply button. This is very important. If you set up all the values and if you leave the element without clicking on apply, then nothing will be preserved. So you have to click on apply. And if you want to see your how the design looks like with your parameters, you can click on viewer button under the element editor. So this will show you your 3D viewer for your iris. So now you can turn it from by pressing the left mouse click, and then when you are pressing left mouse click and turn around the mouse, and then you can see the design in 3D, right? So this is the iris, and I would close it for now. And if you want to know more about this element, you can click on help button. Again, at the bottom of this element editor, there's a question mark, and then you can click on that one so that the help for this particular element will come up. So you see it, and you have more description. For each and every parameter, you can see the description of this particular element. Okay, now we have set up one iris. Now I'm gonna make a copy of the same iris. So I am gonna either you can right mouse click on the on this element, select the iris, and then right click, and then click on copy, or you can simply use Control C, Control V. So copy and click on left click on the empty space on the schematic, and then right click again and then paste. So you will get a copy of the same element, and I'm gonna move it a little bit further, the second one, right? So and now now we have constructed two irises. You see the graphical representation is a little bit different, because I'm not sure if you got the version 10 or version 11. I think version 10 maybe, because we have our latest, I have the latest version on my computer. We have changed sort of a graphical interface there. So this presentation was done with a somewhat earlier version. So that's why the iris representation, graphical representation is a little different, but it's the same thing. So now we have two irises placed, but you see we haven't included the ports yet. So let's add the ports. So again, if you go to the left side of the software, on the top of the library panel, you see this red circle. So left mouse click on the red circle and then place it one time on the left side, and then again click on that red circle, and then again left mouse click on the schematic on the right side. And now you see, okay, we're gonna do a little bit cosmetic thing. So this has to be rotated by 180 degrees. So for that, you can see several ribbon tabs on top of the software. So go to Design tab, and then there you see this rotate selected element icon, as I have shown you on the mouse click, and then click on that one 2 times. Then it will be rotated 180 degrees. Or else you can simply you can use this green dot to rotate it, same like other software. And now we have 4 elements have placed now. So if we go back to our presentation, we are still missing 3 other elements, you see. So they are called empty waveguides. They are not actually they are not visible on this design, except this middle one, but they are placed on the software as a connecting to connect those 2 irises together. So for that, this is the last step. And if you're still under this design tab, you see there are several connecting modes, and I'm choosing the easiest one. It is called connect all unconnected elements straight. So when I click on this, so you see this all closed three dots. This icon, when you click on this icon, you see those three additional components have automatically placed, and then they are connected with the wire. Now the circuit is completed. But still, there has to be one more thing which needs to be done. As you can see on the presentation, we are missing the dimension for the cavity in the middle. The cavity has a certain thickness. So we have to set this thickness for the cavity. And for that, we have to double click on this middle, we call it waveguide, empty waveguide. If you double click on the empty waveguide, on the right hand side, the element editor corresponding to that empty waveguide will appear. And there you find a geometry called L. This is the length of this geometry. So there you can type maybe L1. L1, and then click on apply. L1, and you have to press enter, because L1 is not defined under the variable. So you will be asked to enter the value for the variable. So for L1, maybe you can give a number like 5 or something. So click on OK, and then click on apply. Don't forget this apply button. And you see, once you enter a value for the empty waveguide, it changes its shape, because it's no longer an empty waveguide, but it has a certain thickness. And now we are all set. And now we can view the whole 3D viewer for the whole circuit. For that, if you are still under this design tab, there is an icon called netlist viewer here, as I have shown you with the cursor. If you click on that one, then if you have set up everything correct, if there's nothing wrong, you will get this 3D viewer. Otherwise, an error message will pass to this message tab. So you have to look what is the error. So, and pressing the left mouse click, you can move this, and then you can see this is somewhat similar to what we have seen in this presentation. So you see, I must look, what is the, yeah, okay. I will change the length of this cavity a little bit longer, because it has to be a little bit wider to see this frequency response in the selected frequency range. So for that, I close this 3D viewer, and now you are under the library tab, under the project panel. So you have to click again the projects. Project tab. You go to the project tab again, and now you see there are more variables which has been added. And double click on this L1 variable, and the variable list editor appears on the right hand side. And now you can change the value under the expression. You can change it. I give it 10, and then click on the empty space, and then it will be taken. So if you view the structure again, now you see it is more wider now. Now we are all set for the first cavity, and now we simulate it. For simulation, you see the green button on the top of the software, this green arrow, and it is called Analyze button. And you click on this Analyze button, so then it will analyze the selected circuit. And now you see, I will change the color so you will see it more proper. Okay, now you see there are two lines has appeared. This is the frequency response, and this is the frequency response of a single cavity. And when you merge 2-3 cavities together, you will see, yeah, 2, 3 more and more peaks here in the schematic. We will do it next. And but this is in principle the frequency response of a single cavity. And this green line means the S21 response. And then this is the insertion loss, and then this is the return loss. Return loss means a yellow color line. So this is S11. Okay, and now let's go back to the schematic. You can switch between the schematic and the frequency response by clicking on the button at the bottom of the schematic or the frequency response. You see the wave sign, and if you click on the wave sign, which is on the schematic, at the bottom of the schematic, you get the frequency response corresponding to that schematic. And if you are on the schematic and if you click on the same button again, you switch back to the schematic. And now let's look what the presentation guides us further. Okay, you see we got the similar kind of response. Yeah, this is a little bit a lengthy description in the in terms of yeah, it has a little theory behind that. We call it a two-port network theory, and I come to this point. I have to. Maybe can you explain it for them for a short moment? Yeah. Ah. So.
So now here the basic idea is now how we have wave side, so field side, input side and an output. So it's basically now what we have done is made kind of a rectangular tube. And the tube of branches that we made. Now from one side you make the port 1, and from the other side you get the output port 2. The idea is when you do this, to make it phased out so the cavity will ensure that reduce some of the friction you can get from the input, that in output you will get whatever remains. Now at the frequency response, you see that S11 means you input something from one port to port number 1 and do a measurement from the same port. Meaning that you get a reflection, right? You send something, you measure from the same input, meaning you get reflection. And as you can see around 14.4, you see a dip, meaning there's nothing in the reflection. Right? Meaning you have you have maximum chance. You can confirm that by looking at S12. You input something from port number 1 and measure something from port number 2. And that is S1 to 1. Yeah, you have the maximum transmission around 40.4.
Gigahertz.
Yeah. So now that's basically the take element, you connect it to your circuit, and it's like a box, right?
Yeah.
Input port and output port. Of course, the input port will be different from what comes out, and what comes out is basically 40.4.
Yeah. So, and now we are going to add more resonators together, and let's see how this response look like, right? For that, I switch back to the schematic, and now I double click on the circuits tab again. So you will get on the right hand side the circuit list editor. There, I'm going to copy this main circuit. I click on the copy button on the bottom, and this copy I'm going to change as my project half, not the main, my project half. So you can follow me, and yeah, and the front you can delete, So now you have two circuits called my project main and my project half. So now on this, okay, now and double click on my project half circuit because, okay, yeah, half circuit, and because we have to change something there. Later, now we have the same parameters for the both irises, and now I'm going to use the symmetry to merge two cavities together. So in order to do that, you have to separate the parameters of both irises. So I choose the second iris and I double click on it, and now I change the width of the iris. This is the essential parameter for changing the frequency response in an using the iris, the width of the iris. So this width of the iris, I call it, instead of A2, I call it A22, representing the second iris. And click on enter. You have to give a value for that. So I give, earlier it was 8, I think. Now I give something like 6, a little bit less than the front iris. So I click on OK. And now remaining all the others same, I click on apply button. And next I go to my project main, and then select the schematic diagram of that. And now I delete the two irises which has been placed previously under the my project main. Okay, so select the first iris and click on delete button on your keyboard, and same like that, click on the second iris and click on delete button. So now the two irises are gone. So for those places, now I'm going to introduce two sub-circuits. So two sub-circuits can be imported by the library tab. So under the library tab, the last node is called sub-circuits. If you expand it, you can find a number of sub-circuits according to the ports. So starting from one port sub-circuit, it goes to 2 port, 3 ports, and so on. For our purpose, we're gonna need 2 port sub-circuit. So I'm going to place it here. So it's same like before. Click on the sub-circuit button, left click, and then click on the empty schematic, and then left mouse click on it, and then the sub-circuit will be placed. So, and now double click on the sub-circuit. You see this element editor, and then in front of the name parameter, you have to left mouse click twice. Then you will be given to select available sub-circuits. So you remember we have created my project half filter. Now we are going to select that half filter as a sub-circuit. So, and click on OK. And then click on apply, don't forget that. And now this sub-circuit will represent this my project half filter, which means one cavity which we have designed previously. And now create a copy of this half circuit, right mouse click and copy, and then click on empty space, on left mouse click, empty space, and right mouse click again, and then paste. And you have to do one more thing here. As we combine two together, you have to rotate the second sub-circuit by 180 degrees. So in order to do that, same like before, under the design tab, I'm going to use this rotate icon. And then you see when it is rotated, this number 2 is mirrored now. And like same like before, you click on this icon, connect all unconnected elements straight. So once you click on that, you don't have to worry spending time to connect one by one. It will be connected automatically. And now you can view the structure. So under the same design tab, if you click on netlist viewer, now you see instead of one cavity, now you have got 3 cavities. You may expect 2 cavities, but I will tell you the reason. If you go to the half circuit, you had this. You had 2 irises, and in between one empty waveguide with a certain length. This length is represented by this yellow color box, means 1 cavity. And then if you go to the main circuit, you see in the middle there is another empty waveguide which has a certain length, which means altogether you get 3 cavities now. 3 cavities with so 3 cavities and 2 irises with altogether 4 irises, but it has symmetry. So then we have to when we see the response, we are using the identical irises in the middle and then on both sides identical, because it is symmetric. So now let's analyze this. I'm going again under the same main project. Now main project is consists of 2 sub-circuits, and now you click on analyze button again on top, and now you see the responses, different kind of response. And this is a little bit closer to what we have seen at the very beginning as a filter. You remember? You see the S21 response as explained by Lakmal. So it has a decay on both sides, while S11 response is more shrink to a certain band of frequency. So this is we are closer to a band pass filter already. And now, but you see, this response is not perfect. So we have to make it perfect. So in order to do that, we have to optimize this circuit, or in other words, we have to tune the circuit. But we don't know what to tune, right? So in principle, when you want to shift the frequency left and right side, you have to play with the length of the cavity, which means you see the yellow color boxes here. The length of the yellow color box, when you change this length, the frequency, this band will move either this way or that way. And on the other hand side, if you change the width of this iris, either bigger or smaller, this width, we call it a bandwidth. You see this decay from both sides. This width, the band will either shrink or expand. So this is the principle of our RF filter. So now you need some kind of requirement for your frequency. You need your frequency specifications for your certain filter. So I will use this example, and let's see what are their specifications. So this is the what I have explained you. Let's go to the bottom. This we have already done. So this is what I wanted to mention. Yeah, here. Now we are going to add some frequency specifications. It says these are the given specifications. So it says goal functions are, yeah, okay, we have to specify. Here it is specified already. You see some rectangles have been added to the frequency response. This is what we're going to do next as the optimization goals, defining our optimization goals. So for this example, they say the pass band is from 14.2 to 14.8 gigahertz, which means 14.2 to 14.8. So in this diagram, you see the, I will use a cursor. Yeah. So 14.2 means here, and 14.8, let's say 14, so here. So our filter has to be, has to have the bandwidth between these two ranges. At the moment, I would say the bandwidth is somewhere between 14.6 to 16.2. It is too wide, so we have to shrink it as much as possible. So and in other words, we have to bring it down here. And but we want to know another parameter. We want to know how much should be the return loss. Return loss means we will here. Yeah, here it says the matching. With a matching by minus 14 dB. Minus 14 dB means when we take it here, I take a horizontal line. Minus 14 is somewhere here, right? Somewhere here around. So we don't have to. So the matching has all these yellow color lines between this 14.2 and 14.8. It has to be below this yellow color line, must be below this magenta color line between this frequency range. This is the goal. So now in the microwave wizard, you are capable of defining these goals using the optimize editor. So for that, you go to the project tab again, and you expand your circuits node, and you select your main circuit, my project main. And if you expand my project main, you see optimize parameter node. Double click on optimize parameter node. You will get optimize editor. You can expand it a little bit here, and you have to fill up your goals here. So as the optimizer by default it's none. Take this extreme optimizer. This is the fastest optimizer, which is corresponding to this kind of structures. And max iterations 500, it's okay. Max time 120 minutes. It doesn't take that long. And then max error, we will set it to 0. These are not very important at this step because this kind of analysis is very fast. If you run a very complex structure like in 3D FEM, then sometimes the analysis takes 5 minutes, 10 minutes for one iteration. And then all of a sudden, if you realize, okay, something is wrong, you have to stop. But then you have to set this ticked. Otherwise, you have to wait. Once you click on stop, then you have to wait another 10 minutes until the current analysis is completed. For that purpose, you keep tick these things, but we do not pay attention to this for this example. And now we have to define goal functions. For that, click on new button. And when you click on new button, one goal function is available now, and click on the dotted button here, and you have to set up the parameter, and you have to give which parameter you have to tune. So this is for that scattering parameter. It has to be port 1 has to be 1, and okay, it has to be S11 parameter. That's what we are going to define here. For S11, you have to keep port number 1 is 1 and port number 2 is also 1, because as Lakmal said, we are measuring S11 means we are transmitting the signal from port 1 and we are measuring it again from the port 1. So and we are using a rectangular waveguide. You saw the 3D viewer. The port is a rectangle. So it is port definition is rectangular waveguide, port 1, And the mode for the port 1 is H1O. That is the fundamental mode. I think you are learning about modes in electromagnetic theory. So we are in the filter analysis, we are more focused on the fundamental mode because the remaining modes are suppressed by the structure itself. And then, yeah, so you keep them as it is, and then you see, according to your settings, on the red description, it shows you what kind of S parameter response you are defining here. So it is S11, H1O, and H1O. You can see if you're still not sure about it, you can look at your frequency response. It shows you your S11 is H1O and H1O. And then click on OK. Parameter is set here, and it has to be, yeah. So our requirement is S11 response has to be less than 14 dB. So the less, if you click on this expand node, you can select either less or greater or equal. We keep it less, and now we have to give the value minus 14. Has to be dB, that's the requirement, and starting frequency was 14.2 and the stop frequency was 14.8. I think that was the requirement, right? 14.2 to 14.8. Yeah, and now the weight we give 1 as it is. So yeah, and now we have to do one more thing. You have to go to plot settings tab, and there you have to click on goal function button. Then you will see our defined goal function. So I will turn off these cursors. Now you see this is our goal, main goal. This has to be yeah, the return loss has so this yellow color line must not be anywhere else within this square. Yeah, so it has to be, yeah, below that, between this frequency range. And what about S21? Now we have to define S21 goal because this supports the optimization. Now we click, I would take a copy of this. It is easy to change the parameter. We know everything else is same. I only have to change this from 11 to 21. And this, I know as I'm an experienced user here. So in the filter, for S21, you see it's already decaying from the pass band. After the pass band, S21 is already decaying from both sides. So we have to define those decay in terms of S21. So I would give less than 20 dB from sorry, 14.8 to yeah, because it was already okay. I have to set up the stop band first, maybe 15.2, and here it has to be 14.8, something like this, you see. So for the S11, I would define something like that. And then it is, since the frequency response is symmetric, the same parameter would be defined on the left hand side as well. So I keep another copy, and now I set up, yeah, here would be 13.8 to 14.2, something like this. So this is a kind of a yeah, optimized goal. And now we are going to optimize the circuit, but we need optimized parameters. We need parameters to optimize. In order to do that, we have to change some more, we have to add some more optimized variables to this circuit, because you saw it, we have to tune 3 lengths. One length for this one, this length and this length are identical, but we have to add another separate parameter for the length in the middle. So that's what I'm going to do. So double click on the middle empty waveguide of the main circuit, and you see it's at the moment it is L1. I change it to L2 and click on enter, press enter, and then I may give it the number 12. Click on OK and click on apply. And now I think we are pretty much, we have almost all the required separate parameters to optimize, but we still have to change the variables to optimize variables, the necessary variables. So the waveguide housing, A1 and B1, we don't change because it is standardized. It is the standard from both sides, from both ports. We have to keep it fixed. What we are changing is, I will take the 3D view again. What we are allowed to change is the width of this iris, and the length of these cavities, right? So that means we can change A2. I'm pressing the control button, and then I can select the other variables. So what I have selected here, A2, L1, A22, and L2. Those 4 parameters we have to tune in order to bring our frequency response to our defined goals. And for do that, at the moment, all the variables are type of real, which means they are constant. We have to change it to optimize variables. So click on the drop-down menu and select optimize for each and every required variable. So go through this A2, L1, A22, and L2 and change them to optimized variables as I have shown you, right? And then select all those optimized variables again by pressing control button and hold, and then left mouse click, you can select all of them. And you see at the bottom of variables list editor, there is something called edit selection. If you expand that node, you can edit, you can scale the variable values, or you can range it. You can define a specific range for minimum and maximum. So I give around 20% range from the value, 20% range for the minimum and maximum. And I click on range, and you will see all the ranges for minimum and maximum will be around 20% from the value for each optimized variables. And now click on save button. So whatever you do, you often click on save button. So otherwise, so you won't lose anything. And we go to the frequency response again, and now we have to optimize it. In order to optimize, you click on the simulation tab, and there you can select either analyze, optimize, or sweep. Click on optimize under the simulation tab, and it has to be a parameter analysis. Otherwise, it is also possible to do a field simulation or resonance analysis too. They are somewhat advanced usage. So for now, it's optimize and S parameter analysis. And now click on this big green button on the left corner. Now will start optimizing the circuit, right? And while it is optimizing, you can see the progress. If you go to the bottom of the software, you see several tabs, and there in the corner you see optimized monitor, the bottom. If you click on the optimized monitor, now you see it is how the progress is going on. And now you see this A22 is going down, and okay, it's changing. But at this moment, now you see we are losing one resonance already. At this point, we have to stop it, because here, if we keep in this way, if we keep it going optimized, you will lose this resonance, and then you never will meet the optimizer. So you have to play around with some kind of a manual tuning first, in order to bring somewhat the all peaks somewhat closer to the band, and then you start the optimizer. So now we may have a look what has been changed, deviated very much. So it is probably, yeah, it is probably this parameter, which is this, maybe this is 5, is too small. So I would maybe keep it to 6.5 maybe. Did it work? No. Here. Click on this one and maybe 6.5. I keep it that. And the length was L11 is 8 and this was 12. Yeah. This is, I think, maybe L11. So there's a lot of things. Okay, you have to come up with practice. So I would try to make it again. So you say it is too wide, so you have to shrink when it is too wide. If you want to narrow it down, you have to get the iris, the width of the iris smaller. If it is too narrow, you have to expand the width of the iris. So I would maybe 5 and 4. Let's play around. So. Okay, too long. Okay, maybe I need, okay, so here maybe I will need some more optimized goals, because not to lose this any further here, because here I have to look. Yeah, let me check. Let me check their values, because I did not go through the values exactly. Okay. So. Yeah, so I'm gonna add some more goals here, because that's how here it has been done. You should not, yeah, it has to be something, some more goals need to be added. So I'm gonna ten. So, from this point, you can play around. If you can get You can play with the optimizer to get this this nice curve like here. In the end, it has to be look like this. So you have to see these three zeros and two poles matching to this frequency goal. So I will. This I copy again and yeah, this would be 14, 16. Yeah, something like this. So let's take a look. What did I? 14, 8. No. Okay. Okay, 10, 10, and 20, 14, 14, right? Yeah, now. So now let's do the optimize again. And at the same time, I'm gonna stop it again because at the same time, we can set up more weight to S11 here because this pole, I will change the color of this pole to dark blue. And I'm gonna give more weight to this one. So two, I'm gonna set up again. So I give, so you can set up the weight for a specific goals because then it is more focused on that particular single goal because our main task is to set the return loss to minus 14 dB around this frequency range. So we have to give more weight for that. Now you see slowly it comes to the target, but it may still, it may be too wide because the order of the filter, as I said before, it's corresponding to the number of cavities. We have 3 cavities only. So sometimes it can happen the 3 cavities are not enough. We have to expand the number of cavities. It may not be crucial for this example, but when you have a wider bandwidth for your filter, you may need more and more cavities to satisfy this requirement. Otherwise, you will not you will not meet the exact specifications. And you have to keep monitor your optimized parameters at the same time, because you already see this A2 parameter is now in its 80% in its upper limit. So you may have to increase the upper limit further. And now you see it's, yeah. But you see the goal, we are approaching the target slowly, right? So yeah, in short time, you will reach the target already. So yeah, so we can, yeah, now you see the A2 is very at very low level. So I'm gonna stop it again, and I'm gonna I would get the variable list editor, and if you double click on the yeah, optimized parameter, this required parameter, this will highlight here. And if you click on range again, then you will see it moves up again. And then you can start your optimize again by clicking on optimize, and yeah, do the optimization. Yeah. Okay. Yeah, so in the end, you will see, while you will see it, the target will reach something like this in the end. So this is a simple example for a filter design using µWave wizard. And now you know how to design a filter. And a few, yeah, 2-3 slides I have to show you, because you are familiar with this kind of a circuit, right? You know what it is called. It's called a ladder circuit. So this is the, yeah, basic representation of any filter. And the RF filter, the resonator concept is developed by starting from this point, by going through several conversion process, and it comes to this resonator representation. So this is what I can show you in the next slide. So this is the ladder circuit, and it has gone through several conversion process from the ladder circuit like this. This you have to learn a little bit to get to know about the theory behind this. And then in the end, these, yeah, it can be converted to a representation of resonators like this. And this resonators, what we have built in terms of this rectangular boxes in the yeah, wizard. This is an example of a microstrip filter. These are called horseshoe type resonators. And again, these can be represented by a ladder circuit. And this is called a coupling matrix. I don't think that I have enough time to cover it now, but maybe Lakmal will further arrange it for you also. So then this has to be, yeah, spend some more time on it. But this is also another representation for the ladder circuit. And this has a different kind of a technique, like every filter can be represented by this kind of a matrix, depending on the filter order. Like we designed a third order filter previously having 3 resonators, and this representation is a 6th order filter, and it has exactly 6 rows, and together with 2 more rows for input and output. So this is the called coupling matrix, and this is also widely used for the synthesize techniques, but you can go through it a little later. So that's pretty much it. And if you have any questions, or if you are totally confused of what I have explained, so you can ask me anything. It's if you are interested, then you can play around with the software, and I think you have got or some of you or have got the access to the software, and You can play around with it, and if you have questions, you can ask me. You can get the contact through Lakmal, and I'm happy to help. So yeah, good luck.